All right, hello everyone, and welcome to the second semester of Organic Chemistry Lab. The previous lab was the IR spectroscopy lab, and if you remember from that lab, the goal of that lab was to figure out what the functional group of an unknown molecule is. So this week, we're continuing that trend, so we have a similar goal, which is to identify the functional group, but we're going to use a different technique, and this time we're using a wet lab technique to test the solubility of an organic compound. Now, most organic compounds tend to be very lipophilic, so think oil or cooking oil, and they don't dissolve very well in water, at least at room temperature. So we can exploit that phenomenon and we can examine organic molecules in terms of whether or not they're soluble. So for example, in water, if organic compounds have a carbon to oxygen ratio that is less than 4, we can say that they tend to be soluble. Conversely, if the carbon to oxygen ratio is 4 or greater, then we can generally assume that the organic molecule is insoluble in water. Now, this of course is because of the phenomenon such as like dissolves like. So polar solvents such as water like to dissolve polar substances like table salt, sodium chloride, but water does not like to dissolve lipophilic compounds, hydrophobic compounds, because it's not similar in polarity. This is, however, can be changed if the functional group on the molecule can be ionized. So ionizable functional groups typically means acid or base. So if your compound has an acidic functional group, such as a carboxylic acid, it can be solubilized in water if that water contains a base. So, and vice versa. So if the functional group of your molecule is basic, such as an amine, it can be solubilized by adding it to an acid. And that's something this lab will investigate. So as you can see, we have 5 solvents today. The 5 solvents are sodium bicarbonate, baking soda. There is sulfuric acid, hydrochloric acid, sodium hydroxide, and water. So those are the 5 solvents we're going to be used to play around with our compounds. And these are the compounds we're testing today. So these are known compounds, and we're going to test to see if our rules hold up. So the first compound we're going to start with is butanol. So 1-butanol actually has a carbon-oxygen ratio of 4 to 1. So there are 4 carbons, 1, 2, 3, 4, and 1 oxygen. So we would assume that butanol is insoluble in water. So if we take a vial of water, and this is how it's done normally in the lab, you take a test tube of water, it's about 1 milliliter, and then you take an unknown, or you take your known, in this case it's a known compound, butanol, and you place a few drops inside the test tube and observe if it dissolves. So place a few drops. Okay. And if you can see, if I agitate the test tube, and that's normally done by placing the tube between your thumb and forefinger and then flicking it like this, you can see that they don't mix perfectly. You can see very small pockets of 1-butanol that don't dissolve fully into the water. And given enough time, they will settle towards the top of the solution. So I'll add a little bit more so it's more visible. Okay, so there we've got a thicker layer of 1-butanol floating on the top, and no matter how much I mix it, they're not going to mix. It's not soluble in water, and eventually, given enough time, it'll settle out. So that was the control test, if you will. So that's water with no ionizing agents. The water is neither acidic nor basic. If you look at the butanol structure, the functional group is an alcohol. It's an OH group. Now, the OH group can be ionized, but it doesn't ionize very well unless you have an extremely powerful base, such as sodium hydride or LDA, something like that. But if you're going to use something like sodium hydroxide to try to deprotonate it, that's not going to work very well because the equilibrium is about the same. So with 1-butanol, we would expect it to be insoluble in bases as well as acids. So OH is pretty inert. So we have some, we have some hydrochloric acid here. Okay, we have some sodium hydroxide, and then we have some sodium bicarbonate. So none of these bases and acids are able to ionize the 1-butanol molecule. So if we take our test tubes, and then I'm going to place a few drops into each test tube. Okay, as you can see, they all form layers. So from left to right, we have hydrochloric acid, sodium hydroxide, and sodium bicarbonate. So If we agitate these and try to get them to dissolve, they're still not going to dissolve. So they still form a insoluble biphasic mixture. So the alcohol group cannot be ionized by any of these, HCl, sodium hydroxide, and sodium bicarbonate. Okay, so we'll place these to the side. Okay, but the final solvent we're going to use is concentrated sulfuric acid. Now, concentrated sulfuric acid is much like a chemical baseball bat. What it does is it ionizes even inert functional groups or even neutral functional groups such as the alcohol. So because the acid is so concentrated, it can even protonate the OH group, which makes it charged, and if it's charged, it's more polar, and thus it should be soluble in water. So if we take our 1-butanol, okay, I'm going to place some into this test tube. Okay, we shake it around. Okay, as you can see, it's fully soluble. So if we get our control sample, we get our water. So here's our water. You can see that on the left, the water sample has 2 phases. So the butanol is not dissolving in the water, whereas in the sulfuric acid sample, it is fully dissolved. So under these conditions, if you have a compound which doesn't dissolve in water or in dilute acid, HCl, bicarbonate, or sodium hydroxide, but it does dissolve in sulfuric acid, that we know that it is in fact an alcohol. Okay, now let's move on to our next compound. All right, so the next compound we're going to test is alpha naphthol. So this functional group is actually an alcohol, but it's a special kind of alcohol in that it's connected to an aromatic ring. So because it's connected to the aromatic ring, this OH group is actually a little more soluble than a regular OH group that's connected to an alkane. So we'll see the difference in its solubility in our tests. So just to be certain, we'll start with our control again with water. And this, by the way, is the alpha naphthol. It's a solid brown powder. So we'll open the vial here. We'll take a few crystals or a few bits of solid and we'll place them into the test tube. So there's a little straw here. Okay. Okay, and as you can see, maybe I'll put my hand behind it. You can see that the solid is not dissolving in water. And once again, that's because the carbon-oxygen ratio is too high. There's too many carbons compared to oxygen. So this is our control. It's not soluble in water. Okay. So in acid, so because the phenol is an acidic functional group, it's not going to react with a dilute acid such as hydrochloric acid. So place some in here. It's not going to ionize it. That's our prediction. And we agitate it. And as you can see, they're still solid. So hydrochloric acid does not dissolve alpha naphthol. Okay. And now we get to our interesting solvent, our sodium hydroxide. So sodium hydroxide is a strong base, and it is capable of deprotonating phenols. So phenols are OH groups, alcohols that are attached to aromatic rings. So with this, we would expect it to dissolve. So we take our crystals, place them in, and then we agitate. And as you can see, it has fully dissolved. So we'll get our control, we'll get our water. So water is on the left. You can see some solids floating around. And then on the right is our sodium hydroxide. So our sodium hydroxide is a strong base. It's capable of deprotonating the naphthol. It turns it into an ion, and the ion is soluble in polar solvents in water. So there you go. Now, interestingly, if you now take the alpha naphthol and you react it with a weaker base like sodium bicarbonate, the sodium bicarbonate is not a strong enough base to deprotonate it. So we would expect it to be insoluble in weak base. Okay. Yep. And as you can see, it's even clumping up here. I think I put a little too much in there, but suffice it to say it's not dissolving. So we can compare it here. So here's our sodium hydroxide, our strong base on the left, fully dissolved, and then our weak base on the right, which is insoluble, does not dissolve. Okay. And then for the sake of being thorough, we can test sulfuric acid. So sulfuric acid will solubilize 1-butanol. as we previously discovered, it's neutral. So naphthol will also be solubilized by sulfuric acid because this OH group can actually be protonated by a concentrated acid, such as sulfuric acid. But another reaction that could actually take place is that a sulfate group actually gets attached to this ring, which is something you'll learn about in the lecture. So we expect this to be soluble in sulfuric acid. So here you go. In fact, you can see a color change. Yep. So sulfuric acid has dissolved the alpha naphthol. Though the key takeaway for this is that weak organic acids like phenols can only be solubilized by strong bases like sodium hydroxide. They cannot be solubilized by weak organic bases like sodium bicarbonate. Okay, let's move on to our next compound. Okay, all right, so the next compound we're going to test is benzoic acid. So benzoic acid is a strong organic acid relative to phenols. So this one is an actual carboxylic acid functional group. So this acid is much more acidic than alpha naphthol. Once again though, we're going to begin with testing with water, and as you can see, there's far more carbon than there are oxygen. The ratio of carbon to oxygen is very much above 4. So we can take our water for our control, take our benzoic acid. So benzoic acid is a white solid. And if I can grab some here, oops. Kind of hard to get a hold of. There we go. Place them in. You can see they're floating, so we'll try to agitate it. Okay, as you can see, they don't dissolve in water. Okay, insoluble. For hydrochloric acid, so once again, dilute acids don't really react with organic acids. It has to be the opposite. So if we take hydrochloric acid and benzoic acid, it's not going to ionize it. So we would expect this to be insoluble. So we'll add a few crystals. Okay, and it's still insoluble. So it doesn't dissolve very much. Okay, now we get to a strong base like sodium hydroxide. So sodium hydroxide is a strong base, and when we react it with a strong organic acid, it will deprotonate the benzoic acid, which makes it soluble. So we expect this benzoic acid to dissolve in sodium hydroxide. So you can see some crystals right there. And once we agitate it, we can see that it's dissolved. So I had to agitate it quite a bit because the crystal size of the benzoic acid is quite high. But compared to our control, oops, sorry, that's the HCl. Compared to our control, so our control's on the left, our water, you can still see the crystals floating, or somewhere at the bottom. And then on the right is the sodium hydroxide. So the sodium hydroxide has dissolved the benzoic acid. Now, interestingly, if you have a strong organic acid, so carboxylic acids, if you have a carboxylic acid, it will dissolve in both sodium hydroxide and sodium bicarbonate. So even a weaker base like sodium bicarbonate is capable of dissolving benzoic acid. Okay, so add a few crystals. And another thing to look for when you put acids into sodium bicarbonate is if they have bubbles. So when sodium bicarbonate reacts with acids, it usually generates carbon dioxide. So look for that. Okay. So this one is kind of hard to tell, but if you can see some bubbles, they're very tiny bubbles that are surrounding the crystals of sodium, benzoic acid. So even though it's not going to fully dissolve, we can see that it is in fact dissolving because of the presence of some bubbles there. So those are CO2 bubbles coming out of solution. Given enough time, and perhaps if we heated it or crushed the benzoic acid before we added it, it would in fact dissolve. So benzoic acid and carboxylic acids tend to be soluble in sodium bicarbonate. Okay, and then finally, sulfuric acid. So with concentrated sulfuric acid, I guess we can say that it's dissolving maybe a little bit of the crystals. but not the same way that it does alpha naphthol. So sulfuric acid doesn't tend to react that well with carboxylic acids. Okay, so the next compound we're covering is aniline. So aniline is a weak base, organic base. So this nitrogen has a lone pair that can be protonated, and when it is protonated, it can be ionized. It can be brought into solution brought into aqueous solution, so water, in the presence of an acid. So if we just take aniline and we mix it with some water, once again, the carbon to heteroatom or carbon to oxygen ratio is very high, so we expect it not to dissolve. So we'll place some aniline in the test tube. Okay. And as you can see, it doesn't dissolve. Okay, so this is our control, insoluble. Now, if we take our aniline and we mix it with an acid, so hydrochloric acid, the hydrochloric acid will protonate the aniline. So the functional group on an aniline is the amine, so the NH2 group. And the HCl should protonate that group and turn it into an ion, which can be dissolved in water. So when we agitate this solution, it should dissolve, and there you go. It dissolves to give a kind of a pink color. So if we compare that with our control, so our water on the left, and then our hydrochloric acid on the right. So on the left, it's insoluble, and on the right, it's soluble. Okay. If we try now with bases, so sodium hydroxide and sodium bicarbonate, bases don't react with other bases. So in this case, we would expect them to both be insoluble. Yep. So just like our control, neither of the bases will dissolve aniline. So none of them, neither sodium hydroxide or sodium bicarbonate is capable of ionizing aniline or amines. Okay. And then finally, we have our sulfuric acid. So sulfuric acid, this is sort of similar to naphthol. Sulfuric acid is an acid, so it will protonate the amine right here to form NH3+. But it could also perform a sulfonation, so it might attach a sulfate group to the ring here. So with sulfuric acid, we would expect it to be soluble and perhaps expect a bigger color change. Yep. In fact, you can see a pretty violent reaction there. In fact, it forms a white solid, so it's probably actually reacting more than it is protonating. So it's actually attached a sulfate group somewhere on the ring. Okay. Though that's not the main point of looking at amines. The point about amines is that they tend to be soluble in hydrochloric acid. That's the key takeaway, because they're basic. Okay. All right, the final compound we're taking a look at today is paradichlorobenzene. So the functional group on this molecule is a halide, so chlorine. It could also be bromine or fluorine or iodine. And these functional groups fall into the class called inert functional groups. And they're called inert because they are not soluble in any of these solvents. So we have our paradichlorobenzene here. It's a white solid, much like benzoic acid. And we have our remaining solvents to try. So we would expect this compound, because it has an inert functional group, to be insoluble in all of these solvents. So in fact, I'll just add a little bit to each tube here, and then we'll compare. So I'll take a little bit. So the halide group cannot be ionized by any of these solvents, which is why it remains insoluble. Okay, so if we look at our water, you can see the crystals floating around there. So insoluble in water. Okay. In hydrochloric acid, you can see the crystals floating around, still insoluble. In sodium hydroxide, they're still insoluble. Okay, in sodium bicarbonate, insoluble, not really dissolving. And then finally, in sulfuric acid, even sulfuric acid is not capable of dissolving the paradichlorobenzene. So right at the top, you can see some of the crystals there. Okay, so as we predicted, inert functional groups such as halides are going to be insoluble in all of these test solvents. Okay, so just to briefly recap what we covered, so we'll go by the functional group. So in 1-butanol, which is an alcohol, the key takeaway is that these are soluble only in sulfuric acid. So alcohols tend to fall under the neutral functional groups, which tend to be soluble in sulfuric acid. Naphthol, which is a phenol, so it's an alcohol attached to a ring. These are weak organic acids, and they dissolve in strong bases only. So only in sodium hydroxide do they dissolve. That's the key takeaway. Benzoic acid, so if you have a carboxylic acid, which is a strong organic acid, these will dissolve both in sodium hydroxide and sodium bicarbonate. Okay. Weak bases like aniline, so organic bases, these are soluble in hydrochloric acid. And then paradichlorobenzene, so inert functional groups such as halides, are insoluble in all of these test solvents, so they cannot be ionized.